There's a light switch in your house that's smarter than it looks. Say you've got a staircase, one switch at the bottom, another at the top. Flip either one from either end, and the light changes state. Walk up with the light on, flip the switch at the top, and it turns off. Walk back down, flip the switch at the bottom, and it turns back on. Every single flip of either switch changes the light. That's not both switches have to agree. It's not either one alone is enough. Either. It's a genuinely different question. Not what either switch is doing, but whether the two of them match or don't. That's the gate we're building today. Last episode ended with a promise. Not and or every gate so far, rebuilt from nothing but NAND gates, wired different ways. One gate, wired one way, made not. Two of them, wired differently, made and. Three of them, wired differently again, made or. And then I told you there was one gate that same trick doesn't build cleanly. This is that gate. Here's why the count kept climbing. 1, 2, 3, and why this one breaks the pattern. Every gate you've built so far was really just invert something you already have. Not was one NAND, inverting the single input you were handed. And was that same NAND, then a second one inverting its answer back. Or was two inputs, each inverted first, then combined by a third. In every case, every signal you needed, the input or the answer, was already sitting right there. You just had to flip it at the right moment. This gate can't cheat like that. Think about what it actually has to know. Not just what the first input is, not just the second, but whether the two of them match. That's not sitting inside either input by itself. It's a relationship between them, and nothing you've built so far can see a relationship, only a single signal. Quick guess before I show you, how many NAND gates does do these two match actually take to answer? 4. Here's the wiring. First NAND, plain and ordinary, both real inputs straight in, think of this one as the referee. Second NAND, your first input again, paired this time with the referee's answer. Third NAND, your second input, paired with that same referee. And the fourth NAND takes those two results and combines them one last time. That fourth gate is the one that actually answers the question, and it needed the other three just to gather enough information to ask it. Let's walk one case through, so this isn't just a diagram. Start with both inputs off. The first NAND sees two lows, so it goes high. The second NAND takes that high together with the still off first input, and it goes high too. The third does the same with the second input, also high. The fourth NAND takes those two highs, and it's the only case where a NAND actually drops, output 0. Both inputs matched, so XOR lands on 0, exactly like it should. Now flip just the first input, high and low. The first NAND still sees not both, so it's still high. The second NAND pairs that high with a now high first input. This time it drops to 0. The third stays high. The fourth NAND takes a 0 and a high, and this time it goes high. The inputs differ, and XOR says so. 4 rows, same as every gate before it. Both low, they match, off. First high, second low, they differ, on. Second high, first low, same story, they differ, on. Both high, they match again, off. On exactly when the two inputs disagree. Off exactly when they don't. That's the whole gate, which is exactly why it's called XOR, short for exclusive OR. Either one, but not both. Every gate gets a symbol, and XORs is the OR shield you already know, with one extra curved line traced just behind the first. Same story as always. Two lines go in, one line comes out, and that second curve is the only clue this particular gate is pickier about which two lines it lets through. And XNOR, exclusive NOR, gets built exactly the way you'd now expect. Because you've seen this trick 3 times already. Same 4 NAND gates, plus one more tacked onto the end, wired as a plain inverter. Same move as AND, same move as OR, same move as NOT. Flip XOR's answer, and you get a gate that's on exactly when the two inputs match, and off exactly when they don't. The honest mirror image built the exact same way every inverted gate in this series gets built. Where XOR's whole personality is, tell me if these two disagree. XNOR's is the opposite job. Tell me if these two are equal. That's not just a cute reversal. It's the literal circuit engineers reach for anytime a machine needs to check whether two bits actually match, one pair at a time. Compare two numbers a bit at a time, and XNOR is the gate doing the comparing. You've probably used this gate constantly without ever putting a name to it. That staircase switch from the start of this episode isn't a metaphor. It's real. working XOR logic, wired into the walls of ordinary houses, older than the transistor itself. In code, XOR shows up as a single character, the caret, and it's the operation behind a genuinely blunt trick. XOR any value with itself and you get 0 every single time, no matter what the value was. XOR that 0 again with the same second value and you get your original answer back untouched. That one property, cancel with itself, flip back with a repeat, is the entire idea behind the simplest form of encryption that exists. Scramble a message by XORing it with a secret key, and unscramble it later by XORing with that exact same key a second time. Real encryption is more careful than that. Where the key comes from matters, and reusing a simple key like this isn't safe. But the canceling trick underneath it is real, and it's genuinely powerful. That same cancel with itself trick has a second-party trick built into it. You can swap two variables' values without ever using a third one to hold either temporarily. 3 XOR operations in a row, no spare storage, no extra step. It looks like a magic trick the first time you see it. It's just this same gate, 3 times. It's clever, but it's mostly not how you'd actually write this in modern code. The point isn't the trick, it's that this one tiny gate has an algebra of its own. Hang on to this shape because it comes back. Not today, but the moment this series starts teaching these gates to actually add numbers together, XOR is going to be sitting right at the center of it. That's still a good ways off. 6 gates now, counting NAND and NOR, 7 with XNOR. Every one of them built from nothing but a switch and eventually nothing but NAND. What's still missing is the math that ties all 7 of them together on paper without drawing a single wire. That's Boolean algebra, and it's next.